Okay, we're going to talk about instantaneous velocity today. But first, let's review what we mean by velocity, what we mean by average velocity, because that's what we dealt with before. So let's review a little bit. What we defined average velocity to be from Unit 1. Well, and by the way, this works all the time. I'm going to put a little AV there for meaning average. Average velocity, by definition, is my displacement divided by my time. And so you figure you go x final minus x initial divided by t final minus t initial, and you've got it in meters per second. And that's what we did. And the way we applied this in Unit 1 is this. If you had a position versus time graph that looks something like this is position and time. Let's say, and I'm not going to put numbers on here because it'd take too long, but let's just say you had something where your velocity, well, your position increased at a fairly rapid rate, then you stayed where you were for a period of time, and then you went back where you started fairly quickly. Okay. Now, what we did here is for a period of time, and this represents time here, so for a certain period of time, my average velocity was, well, my velocity stayed constant from here to here. And I could figure out what that velocity was by just taking a little slope. And a little delta x over delta t. Okay, let me zoom in so you can see what I'm writing. So we just took a little slope here. And then we saw, oh, the slope here is 0, and here the slope is negative. So we could draw a velocity versus time graph, right? And we say, oh, okay, right here, the velocity is positive. And then right here, the velocity is 0. And then for these last couple of seconds, what's true about the velocity? The velocity is negative because you're going back the other way. You're going in the negative x direction. And it looks pretty steep, so I'm going to drop it down like that. So here's what we did. By looking at the slopes of these on this graph, on the position versus time graph, I could get the velocities. And the velocities were constant during each of these little time intervals within that graph. And so I could use this delta x over delta t as a slope to figure out what the velocity is easily. But now we're going to deal with a more difficult situation. In a more realistic situation. Look, objects really don't move this way, do they? You don't move with a constant velocity and then instantaneously stop. If you did, it would shatter every bone in your body trying to do it. Okay, and then go from 0 velocity to some negative velocity with no time going by, instantly changing your velocity from 0 to negative 5 meters per second. Again, every bone in your body shattered. Okay, this is fatal right here. So what actually happens in the real world is that you take a little bit of time to change your velocity, to slow to a stop or speed up, in a negative direction. So in other words, your velocity changes gradually. It doesn't change instantly from one value that's positive to 0, or from 0 to some value that's negative. It takes time. So this is really what I'm going to show you now is really what we're going to have is something like this. So here's position, and this is time. So let's start at the origin. Not at the origin. Let's start right here. And then we'll go like this. we'll go, and then we'll slow down. And then we'll, so let me make that a little bit, t-axis a little bit longer. I mean, here's what this, here's a graph of the motion of an object. And this is a little bit more realistic about how you might move back and forth along a straight line. So you start off with some velocity. You're moving along the x-axis, right? And then you slow to a stop, and then you go backwards, you slow to a stop, and then you move forward again. Okay, do you see that? You know, if I give you a graph like this, can you act it out? Can I hand it to you and you can stand at an x-axis and actually walk the graph out? Remember, all the motion is along a straight line. We're still dealing with one-dimensional motion right now. So you're moving, you slow down, slow down, slow down, stop. And then right here, what happens to your motion at this point right here? Well, before you were moving away from the axis in a positive direction, and after you're moving back towards the origin in a negative direction, right? So what happens right here? You change your direction of your motion. And then you're moving back towards the origin, moving back towards the origin. And then what happens right here? You change your direction again, and you start moving away from. So this is somebody who can't make up their mind. They're moving away, then they back up, and then they go forward again. But it's very realistic. You do this sort of thing. Now, how are we going to draw the velocity versus time graph for this? Well, this gives us we have to use the idea of instantaneous velocity. You see, when I was using this graph over here, look at the slope. Do you see that the slope is constant, 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 and then boom! Slope changes, and then slope is constant, slope is constant, slope is constant. But what's happening to the slope on this graph? The slope is gradually changing the whole time. So I can figure out, well, what's the slope right here? The slope right here, you see it's positive, and it's pretty fast. It's pretty steep. So I'm going to say, okay, that means my velocity is pretty fast and positive. But what's happening to the slope of these little tiny line segments as I move along the graph? What's happening to the slope? Is it staying the same? No. If it stayed the same, what would this look like? It would look like a straight line. Is it getting steeper as I move in through time? No. It's getting shallower. Which means what is happening to my velocity? We're slowing down. We're slowing down. And when have I stopped? When have I stopped? Right here. You see right here? You're changing directions, right? If you're walking up and down a straight line, and you were moving forward, and then you're moving backwards, somewhere between moving forward and moving backward, you had to stop. Does that make sense? And where do you stop? You stop right here, and you can see it because the slope right here is 0. Remember, and we should write this down. The velocity graph describes the slope of the position graph. Okay? So what I'm going to do is I'm going to draw a graph. This graph is going to describe what's happening to the slope of this graph. Now, really what I'm doing is I'm taking a derivative That's what this graph is going to derive from this graph. That's why they call it derivative. But it's derived from the slope. So here we have a steep positive slope. And then right here, the slope is 0. So one thing I do is I say, okay, here at this time, the slope is positive. So I put a positive slope. And here it's 0. And it gradually decreases to 0. So the velocity is going to kind of look like this. But then what happens right here? The velocity becomes what? Look at the slope right along there on this little curve. What happens to this slope right here? Is it 0? No. Is it positive? No, it is negative. It's a negative slope now, which means my velocity is negative. Because remember, the slope of this graph is my velocity graph. So now my velocity is negative. Now look what happens right here. This is an important place. It's called a point of inflection. What's happening see my velocity it starts 0, negative, more negative, faster and faster until I get here. Now what happens to my slope? It starts getting shallower again, right? Shallower and shallower and shallower. So this means it's at its maximum negative slope right here. And now so now it's getting shallower and shallower and shallower until what's the slope right here? What's the slope right there? Somebody give me an answer. What's the slope right there? It's 0, right? Because what am I doing to my motion? I am changing direction. I was moving backwards, but now I'm going to move forward again, so I have to stop for an instant in time. So that means at this time t, my slope is 0 right here, which means my velocity is 0 right here, and it looks pretty gradual, like I gradually changed my velocity from this negative velocity back to 0. And now what happens right here? The velocity becomes positive, 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 more positive, more positive, more positive. So it looks like it's just increasing like this. Now this is qualitative. I'm not using numbers here. You're going to use numbers in just a few minutes when you do assignment 2. But I want you to see that all I'm doing is looking at the slope. I'm looking at the slopes on this graph, and I'm drawing what's happening to the slope right here. Now, we have a definition that we defined in assignment 1 for acceleration. And remember we said that acceleration is equal to, or at least average acceleration is equal to, the change in velocity over the change in time. Okay? This is what we said last time, talking about acceleration. The acceleration is the rate at which I change my velocity. So, in other words, I change my velocity, the time it takes to change my velocity by a certain amount. So this is meters per second every second. How much I change my velocity in meters per second every second. Well, where is acceleration in this graph over here? Where would I get a delta V over delta T? The what? The slope. This is velocity right here. Like, what's the slope of this? Oh. Draw a little slope triangle. This is my rise, my run, and this is the rise, delta V. Now, here, what's true about this slope? It's negative, and this is positive. Okay? So what I can do now from this graph is I can draw an acceleration versus time graph. Now we're going to do this quantitatively, but again, I'm not putting any numbers here yet. So now, what do we notice about the slope all the way down to here? It's constant, and it is positive, negative. It's negative. So therefore, my acceleration all the way down here, I have a negative acceleration. Then what happens to my acceleration right here? It changes to a positive acceleration. And it stays constant. So, this is my acceleration graph, and the acceleration graph describes the slope of the what? Of the, what am I going to put next? The velocity graph. Yes, the velocity versus time graph. I'll just put the velocity graph. Everything's with respect to time. Now, isn't this cool? We have what here, some graphs. I started off by making up a position versus time graph. Somebody just kind of walking forward, then stopping, changing direction, and then stopping and changing direction again. And then we graphed, well, by looking at the slopes of these, and these are instantaneous slopes, which we're going to talk more about here in a second. I got the velocity graph. And then from the velocity graph, I looked at the slope of this, because the slope of velocity with time is acceleration, and I drew my acceleration graph. All right. Now, let's talk more specifically about instantaneous acceleration. And how we are going to figure that out. So let's take a look at another graph. Position as a function of time. And again, I'm not going to put numbers on here just to save time. But suppose it looks something like this. Again. Now, if I want to know what my average velocity is for the whole time, and by the way, this is going to get a little bit messy, so sorry, maybe I'll redraw it a couple times. But my average velocity is delta x over delta t. So if I want to know what the average velocity is for this whole thing, remember, somebody starts here and they're walking forward, and then they come to a stop, and they walk backwards, and then they come to a stop, and they walk forward again. But the average velocity is delta, well, what is delta x for the whole thing? Well, here's x initial, here's x final, and here's delta t. So it's really the slope of the line right here. So my average velocity is a kind of an idea of how fast am I going averaged out over the whole time period. But what if you want to know how fast am I going right now? At an instant in time. Well, I mean, this is the velocity that you're used to, right? You drive a car and somebody says, how fast are you going? Well, you don't say, well, I have an average velocity of 30 miles per hour over the whole trip. And people look at you funny. Because how would you know? I mean, you'd have to figure out what your delta x is and take your time and divide it, and it's crazy. But when somebody says, how fast are you going, what do you actually do? Yeah, you look at your speedometer, right? And say, oh, I'm going 60 miles an hour right now. This instant in time, I'm going 60 miles an hour. Okay? So, how do we figure that out? How do we figure out how fast we're going at an instant in time? Now, I'm going to get into something a little bit more advanced than I need to for this class, but I want you to see it because most of you are going to see it in your calculus classes very soon, this year or next year. But it makes sense. Let's say I want to know how fast I'm going right at this time, t. I'm going to call this some arbitrary time t. Could be like t equals 3 seconds. Well, right now, all we know how to do is figure out average velocities. And in average velocity, I need a delta t, right? Delta x over delta t. So let's add delta t to this. So right here, so I'm going to add delta t. Here to here is delta t. Well, let me give a bigger delta t. Let's big delta t over here. Okay, thank you. Oh, this is the wrong class. This is 902. It's in 901. Okay, so what I'm going to do, let's say delta t is all the way over here. Here's delta t all the way over here. So I go up like this. Oh, yeah, Wakas? Where's Wakas? Is he here? Okay, never mind. I got to do this. All right, so if I go up like this, now what have I got? If I connect these two lines with a straight line, and I take a look at this straight line, what does the slope of this straight line tell me? It tells me my average velocity between this time and this time. Right? It's going to be delta t over delta x. So that gives me an average between 2 times on my graph. But that's not what I want to know. I want to know how fast am I going at this time right here. Not averaged over all these this whole time span. I want to know right here. How fast right there. So I'm going to do a trick. Let's let delta t get really small. There's an old Steve Martin routine. Steve Martin, the comedian, called Get Small. He likes to get small. Anyway, it's probably on YouTube. Look it up. Anyway, delta t, we're going to let it get really small. What's the smallest it can get? What's the smallest time interval you can have? 0. Well, you can't get to 0, but see what this arrow, what does this arrow mean in mathematics? It means let delta t approach 0. It never reaches it, it just approaches 0. So what we're going to do, we're going to define my instantaneous velocity. I'll just put inst for instantaneous. I'm going to say this is equal to the limit as delta t goes to 0. I'm taking what's called a limit here. Don't freak out. It really isn't that tough. Of delta x over delta t. What do we mean by that? Now this is really cool stuff. I'm going to let delta t get smaller. And let's look at what happens to the slope of the line connecting t to t plus delta t. Let's let delta t get smaller. So like, let's say a third as big. So here's my new point, and what happened to the slope? See, here was the original slope, but now I shrunk delta t, I made it go over here, and now when I connect these two lines, I get this line right here. The slope got steeper, didn't it? Which means the average velocity is higher. Well, what I'm actually going to do, though, is I'm going to let delta t get really small. Really small. So let's let delta t get super small. Now we can't reach 0, but I'm going to let it get super small. So it's right here. I'm going to make, here's t plus delta t. I'm going to make it really small. And I come up here and I get another point on the line, and I'm going to connect those 2 points, and I get a line that looks like this. Yikes. Now I'm going to blow this up. This document camera is almost like a microscope. Watch this, it's amazing. I'm going to zoom in as much as I can. Oh, amazing. Oh, now can it focus? Oh yeah, look at that. You can actually see the molecules. No, not really. Now, what I've got here is I've got a little delta t and I've got a little tiny delta x. And I can let delta t shrink or approach 0. Now, what's really close to 0? How about a billionth of a second? Is that pretty close to 0? Yes, it's really close to 0. So let's say my delta t here is a billionth of a second. So delta t is really tiny, but what's true but what happened to delta x? It got small too, didn't it? It got small right along with delta t. If this is a billionth of a second, this might be 2 billionths of a meter. That's okay. Can I divide 2 billionths of a meter divided by 1 billionth of a second? What do I get when I divide 2 billionths of a meter by 1 billionth of a second? It's equal to 2 meters per second. A nice, easy number. So that's what we do in differential calculus. And you're going to learn all about this in your calculus classes. But when I allow these 2 points right here to merge, never quite merging but almost merging, and take the slope of the line, you get what's called the slope of the tangent line. The slope of a tangent line. The instantaneous velocity is the slope of the tangent line on a position versus time graph. So I'm going to redraw this because it got all messy. Position, time. So here's the graph I drew. What if I want to know, and pay attention right now because you're going to be doing this here in a few minutes. What if I want to know what is the slope, what is the velocity at this time, t? Well, here's what you do. You take a ruler, or failing that, just take a piece of paper and fold it, make a straight edge. And what you do is you want to draw a tangent line to this curve. Now here's how you do that. Everybody watch. There's a little finesse, a little technique here. You approach the line. You approach it, getting closer. You only want to touch the line at one point. This point right here. Getting closer. It's like you're going to kiss the line with this. Right there. Okay, that's it. That's it. You see how the piece of paper is only touched? Now, See, there's a little white space right in there. Little white space over here. You want the white space to be the same coming off the curve. Then I'm going to draw this line. Look at that. Beautiful. Well, maybe not perfect, but it's good enough. This is a tangent line. And now I can pick any 2 points I want on that line. Any 2 points I want. I can pick these 2 points. I can do a delta t, delta x. Figure out the slope of that line. When I figure out the slope of the tangent line, I have the instantaneous velocity for this graph. Now what you're going to have to do is figure that out for your graphs. Now who has a nice graph? I should have planned this ahead of time. Who has a nice position versus time graph for number 1, and they would like me to do their first problem for them right here? Who's got a nice graph? Okay, we're being recorded, so let's do this. Yeah, you. Okay, have you got a nice graph? Bring it over here. Don't worry, I won't. For 1. Oh, that's a beautiful graph. Oh, look at this. Look at this. Now, I'm going to do this for you. What you're going to have to do is at each second, here, 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 and here, you're going to have to figure out the slope. Let me zoom out. This is so big, it's wonderful. I'm not kidding. You know, this is really well done. So this was the position versus time graph for number 1 from assignment 1. Okay? So what we're going to do is this. I'm going to calculate the slope at this point right here. And what it's going to do, it's going to give me the instantaneous velocity of the object at 1 second. So now it sometimes doesn't work out just perfectly. That's okay. So see, I'm going to kiss that graph. Okay. Now if that creeps you out, I'm sorry. But look. Hey, everybody look. See how this is the next point. See how it's up? Here's the previous point. See how it's about the same. I only want to touch the graph at 1 point. Now pay attention to this, because you're going to have to do this. If you do it wrong, you have to do it over. And it's a lot of tedious work. So now I'm going to draw a tangent line. So that looks like a pretty decent tangent line. Now what I'm going to do is I'm going to pick the slope. I'm going to calculate the slope of this. I'm going to pick 2 points, and it doesn't have to be, I don't have to include this. I can pick 2 points anywhere on here. And I guess I can pick this point right here, because it starts at 1 second. And maybe I'll go to 3 seconds. So I'll pick this point, and then at 3 seconds, it's right here. So what's my delta t? If I go from 1 second to 3 seconds, what's my delta t? Yeah, 2 seconds. So my velocity, my instantaneous velocity at 1 second is going to be, well, there's my delta t. What's my delta x? Well, this says it was at 1.5? Really? This isn't 1.5. This is more like, yeah, this might be a little off because you didn't graph this point right. So, well, I'll just use whatever you have here. That looks like, about 2. And then what is this? 5, 6, 7, 8, maybe a little over 8, 8.5. I'll just say 8.5. And this is 2. So what's my delta x if I go from 2 to 8.5? What is my delta x? Huh? 6 point what? 6.5 meters. Now, so what is my instantaneous velocity? What is 6.5 meters divided by 2 seconds? 3 point what? 3.25 meters per second. Now, here's the killing part. I already know what the velocity is at 1 second because I gave that to you. What is the velocity at 1 second for number 1 on assignment 1? Look it up. Quit staring at me. Look it up. What was the velocity at 1 second for number 1? It was 3. What did I get? 3.25. That's pretty good. Especially considering that I think this dot should be a little bit lower. I think your graphic's a little bit off. That's pretty good. It's good enough. Okay, I'll tell you what. I'll show you what you're going to do now. From assignment 1. Now here was. Here's the worksheet I'm going to hand out to you right now. I'm going to give you about a half an hour to do this. For number 1, 2, 3, and 4, 1, 2, and 3 from assignment 1, you're going to make a data table like this. So you're going to have 3 data tables that looks like this. This is all you're going to have on assignment 2, are these 3 data tables filled out. At 1, 2, 3, and 4 seconds for each graph, you're going to draw a tangent line. Just the way I just did. Then you're going to show your so at 1, this is going to be 1, 2, 3, and 4 seconds for all of them. Then you're going to show your slope you're going to draw the tangent line, and then you're going to show your slope calculations here. Then you're going to put your calculated answer. Now, what was our calculated answer? 3.25 meters per second. Then you're going to look up what the actual instantaneous velocity was, because I gave it to you in the chart. It was 3. Then you're going to calculate the percentage error. Well, how do you do that? Because you know it's supposed to be 3, but we got 3.25. Well, here's how you do that. It's given minus calculated divided by given times 100%. So it's given, which is 3. So I'll get my calculator out here. It's 3 minus the calculated 3.25 equals, I get negative 0.25, and then I'm going to divide it by what's given, divided by 3. And then I'm going to multiply it by 100 to make it a percentage. And I get negative 8.33%. Okay, now you show your calculations in here, like we did, I did on your paper. That's not bad at all. Some of you with really good graphs, you'll be able to get 0% error. You will really nail it. Your slope of your tangent line will be exactly what it should be. If it's a little bit off, if it's 10, 20% off, even 30% off, if it's more than 30% off, I want you to look at your graph. You might have really messed it up. Okay? So I'll hand these out now, and I'll give you about a half an hour to get this done.